Section 5.5 is about how to solve a rational inequality, which is an inequality that has a rational expression in it. At least one. There can be more than one. You can have two, you can have three. But the big thing right off the bat, I think, is that the way that you solve a rational inequality looks nothing like the way that you solve a rational equation, although you might expect it to. And it would be very reasonable to expect it to because of what's happened already in the course. Because when we had linear equations and linear inequalities, which is what these first two examples are, then the way that you solve them really isn't all that different, right? This one that's on the left, the one that's the equation, I'd want to get the x term by itself, so I'd subtract 19 from both sides. So then I'd have negative 3x is equal to negative 11. And then in order to get x by itself, I divide both sides by negative 3. And then what I'm going to end up with is that x is 11 thirds, right? And then what's the difference with the inequality? Well, you're basically going to do the same steps. The only thing that's going to be different is that when you divide by negative 3, you're going to have to reverse the direction of the inequality. Because whenever you divide by a negative or multiply by a negative, that's going to reverse the direction of the inequality. So you would still do the same steps, right? You'd still subtract 19 from both sides to get that negative 3x by itself. So you have negative 3x greater than negative 11. But then when you divide by negative 3, then the direction of the inequality is going to switch. So you'd have negative 11 over negative 3. So you end up with that x is less than 11 thirds as the answer. All right, so yeah, you got to flip the inequality around, but other than that, it's all the same steps. That is not the way things are going to go. So like this stuff here, there's no analog with what's about to happen. So the reason for that is because with a rational expression, there are a couple of different ways usually where it can be positive or negative. So this in particular, that rational expression that's on the left side, it would be positive if x was bigger than 4, because then you're going to get a positive number on top, you're going to get a positive number on the bottom, right? Like if x is 5, you're going to end up with 1 over 6, it looks like. But what if x is less than negative 1? Like what if x is like negative 10? Then you'd have negative 10 minus 4 over negative 10 plus 1, so you'd have negative 14 over negative 9. That's a positive number. But then in between negative 1 and 4, it's going to be negative. So because there are multiple ways for that to be positive, you can't just solve it like straight up like you would with an equation. That's not really going to work. Because then there are like these different cases that you have to consider. If you try to do it that way, you'd have to break it up into like this like decision tree of like if x is in this interval, you're going over here, and if it's in this interval, you're going over there. It gets really big and complicated. So we're not going to do it that way. So all right, so this is all kind of explaining this example up here where there are two different ways to get that expression on the left to be positive, where you could have the numerator and denominator both positive, or you could have them both be negative. So to be more specific, if x is greater than 4, it's going to be positive. If x is less than negative 1, it's going to be positive. And then I stuck the other stuff in here too. When x is between negative 1 and 4, strictly between, then it's going to be negative because you're going to end up with a negative number on top and a positive number on the bottom. Then when x is exactly equal to 4, you get 0. And then when x is negative 1, the expression's undefined because you'd have a 0 in the numerator. So all those things usually you have to consider somehow when you're solving a rational inequality. And then your solution ends up being either an interval or a union of intervals. Sometimes you end up including an endpoint. Here we didn't because we had a strict inequality because originally there was a greater than. If you have a greater than or equal to, like if we had a greater than or equal to up there instead of a greater than, we'd have to include the 4, right? Because then when x is 4, you do get 0. So if it was greater than or equal to, then you'd have to include the 0. So there's a lot of stuff to think about. And why does this end up being so crazy? Well, we don't really get into the graphing. You will in 151. So if you take 151, you're going to do this. Trust me, I've taught 151. This is definitely in there in the rational function chapter. what the graphs of these look like. They can look a little wild. Usually they come in multiple pieces. So for this particular function, which is the one from the last page, we know that that's undefined when x is negative 1, right? So I'm just going to make a dotted vertical line here to symbolize that. So we shouldn't have any function value along this dotted vertical line. So that's off limits for the function, so to speak, right? So there's x equals negative 1. And then, let's see, if I was going to graph this thing, we know that when x is 4, f of x is 0, so the point 4, 0 would be on it. The y-intercept, so when x is 0, it looks like y is negative 4, that's down here. Another thing that happens, and don't worry about how I would know this right now, when you take 151 and do it, you'll see this part. I also actually have a horizontal line right at y equals 1 that is also going to kind of rein in where the function goes. So what you end up with as a graph, basically those dotted lines sort of fence it in a way, where then, and they're called asymptotes, which you won't really need to know right now, but I guess you'll know it in 151, that word comes up a lot. But basically they kind of like fence in where the function is. So what you'd end up with here, I got a lot of ground to cover. Hopefully I can put a decent arc on this. All right. Maybe something like that. Let me clean this up a little. That's not what I wanted. All right, close enough. So you'd have that piece, but then you're going to have something on the left side too. So I put negative 3 into that function. I got 7/2, so that point is right there. And then that means that if it's up here, it's going to get sort of fenced off up there by the two dotted lines, and you'd end up with maybe something like this. All right, so we said it was positive when x was less than negative 1. That's this part on the left, right? If it's fenced in by those red dotted lines, it's not going down below the axis, right? Because that horizontal red line is above it. So that's where you get the graph being positive. And then when x is greater than 4, because on the piece on the right side, once you go past 4, once you go to the right of it, it's above the axis, right? It's between y equals 0 and y equals 1, but it's positive, right? So that's what that function would look like. And then I put a crazy one in here. All right, so this one, the second one, if you look at the denominator, that's not going to be defined when x is 2 or negative 2. So I would need dotted lines at both of those. So 2 is off limits, and so is negative 2 since they're outside the domain. So I'll just put these in here. And again, you get the horizontal line, the horizontal dotted line, that barrier, so to speak, when y equals 1. It's not always at y equals 1. It just happened to work out that way for these two examples. And I picked ones where I could actually like plot the points where the y coordinates wouldn't go crazy, and they just happened to both work out to where the horizontal asymptote is y equals 1. But I'll just put that in here. And really that's there for the end behavior. So I'm not going to put it in the middle because actually this function crosses over that. But let's see. If I plot some points here, or just kind of put in what we would know, let's see. X-intercepts would be negative 4 and 1. And then the y-intercept is going to be 1, it looks like, because you'd get negative 4 over negative 4. Let's see. Other than that, I guess I need 1 point on the right to figure out if it's on the top or the bottom. If you put 4 into that, you get 4 back out. So 4 is up there. So that means that in this part on the right, in the upper right, that's going to be fenced in or boxed in by those two dotted lines, sort of like that. You get a similar thing on the left, where then it's underneath that horizontal dotted line. And then in the middle, what you get kind of looks like this. It's going to kind of be that sort of shape. It looks a little angular, but that's the general idea. All right, so then for this one, that we won't have to solve any, I don't think, that break up like this, because this would actually, if you were going to do it with a number line, it would break up into 5 pieces. Yeah, that's a lot. So I think we'll have more they break up into 4, but I don't think we go beyond that. But I mean, if you were going to say, like, where is the function positive, x value is less than -4, between -2 and +1, and then greater than +2, right? Like, that's a lot, right? That's a union of 3 separate intervals. But the important thing on this page, like that last thing that I said, I don't think you really need to worry about too much. It was just kind of for illustration. The important thing is the graphs look kind of crazy, right? And you can tell, like, here there are multiple places where you get positive values, there are multiple places where you get negative values. So you couldn't solve an inequality the conventional way and expect it to work, right? However, one other thing that I do want to point out here, give me a different color, maybe brown, that'll stick out, or maybe black, that's even better. So notice right here, right where that vertical line is, it's going from positive values to negative values, right? It's positive on the left, negative on the right. So I'm just going to say positive to negative. And then right here, in the value that made the function 0, it's going from negative to positive. So the only sign changes happen at the values that make the numerator 0 and make the denominator 0. What about down here? All right. Well, at the -2 and the +2, in both cases, it's going negative to positive. So negative to positive, negative to positive. And then at the x-intercept, so right there, it goes positive to negative. And then, let's see, right there, it goes positive to negative. So again, where does the sign change? Either positive to negative or negative to positive. Either where the numerator is 0 or where the denominator is 0. So basically what you do is you find those x values that would make either the numerator 0 or the denominator 0. You use those to break up the number line, and then you just check the sign in each of the resulting intervals in your broken up number line. That's pretty much what you end up doing, which can be a decent amount of work. So what we've got to do, first of all, if it's not set up this way, which I guess so far this is all that we've kind of seen, but you want to rewrite the inequality so 0 is on one side and one single rational expression is on the other. So like if you have 2 rational expressions, get a common denominator and combine them together. Then figure out the values for which the rational expression is either 0 or undefined. So the values that make it 0, those are the values that make the numerator 0. The values that make it undefined, those are the values that make the denominator 0. Then you use those values to break up the number line to intervals, and then you check each interval. You just pick a value in the interval and substitute it in to the rational expression and see if what you get is positive or negative. Because if you know where all the sign changes are, then for that whole interval, it should always be the same sign, right? If you sub in one number and what you get for the rational expression is positive, then that's going to happen for anything in that interval. If you subbed in any value in that interval, you should get something that's positive, right? It's basically that idea. And then make sure if you have a non-strict inequality, so either a less than or equal to or greater than or equal to, something that involves an or equal to, make sure you check the endpoints, because then you've got to include anything that would make the numerator 0. I try to draw that into the number line with like open circles and closed circles, and then or like a filled in circle, I guess, instead of closed. It's weird to say closed circle. Filled in circle sounds better. Anyway, Then that way, if I see the filled in circle, I go, oh, I need to include that. So I'll do that when we start drawing the number lines, which is about to happen in, I think we'll probably have one in about 90 seconds. All right, so the first step we don't need to do with number 1 because we already have a 0 on one side and one irrational expression on the other. So then if we set, I want that in blue, not black. If we set the numerator equal to 0, then that means we're going to have x minus 9 equals 0, so x equals 9. And then if we set the denominator equal to 0, we're going to have x minus 4 equals 0, so x equals 4. So we have to use the 9 and the 4 to break up the number line. So I'm going to draw a big number line here. And then I guess I'll have my 4 back here, and my 9 up here. And we're not going to include either endpoint because we have a strict inequality. It's a greater than, right? So we're not going to include the 4 because that would make the expression undefined, so open circle there. But then for the 9, it's a strict greater than, so we don't need that either, right? 0 is not greater than 0, so don't need it. And then we just have to check each interval. So what we're going to do then, I think I've got enough space over here to write this in, so we'll get our intervals. So the first one is from negative infinity to 4. The one in between is 4 to 9. And then the last one over on the right is from 9 to infinity. Then we're going to need to pick out a test value for each interval. And then for the rational expression, we'll get the numerator, we'll get the denominator, and then what the expression actually is. All right, so for that first interval, I would say that if there's ever a point where you can pick 0, you should, because subbing in 0 tends to be the easiest thing to simplify. So here, that's going to be my test value. So if x is 0, then the numerator is going to be 0 minus 9, which is negative 9. The denominator is 0 minus 4, which is negative 4. So the expression negative 9 over negative 4, same thing as 9/4, that is positive. Right? So then on my number line, I'm just going to put a big plus in that interval. In between 4 and 9, I guess it doesn't matter what you pick, although I would probably advise picking an integer in general, just to make the simplification easier. So I picked 5. So then my numerator would be 5 minus 9, which is negative 4. My denominator is 5 minus 4, which is 1. So for my expression, I got negative 4 over 1, which is negative 4, and that is negative. All right. So then in between the 4 and the 9 in my number line, I'm going to make a big negative sign. And then from 9 to infinity, I would just pick 10, right? You've got to pick a number bigger than 9. I would just pick the first integer just to make the simplification probably less involved. So if I pick 10, then I'll have 10 minus 9, which is 1 for the numerator, and 10 minus 4, which is 6 for the denominator. So I'm going to get 1/6, which is positive. So then that means I got to make a big plus on my number line in that last interval. There we go. All right, so what's our solution? Well, we're looking for where the expression is greater than 0. So in the number line, it's where the pluses are. So on the left and on the right, less than 4, greater than 9. So you could write it a couple of different ways. You could write the solution in set notation or in interval notation. So I'm going to write it in set notation first, which I guess would be the set of all x such that x is less than 4 or x is greater than 9. Or you could write it with intervals. I guess then you'd have negative infinity to 4 union 9 to infinity. And we wouldn't include either of those endpoints here. We're not going to include the 4. We're not going to include the 9. It's a strict inequality, so you never include the endpoints then. But that's what you'd end up with as a solution. The other examples are like this, but perhaps more involved. Like, we didn't have to do the first step in this one, right? It was already set up where we had a 0 on one side and a single rational expression on the other. What if it's not set up for that? That's number 2, where we've got a 2 on the other side. All right, so what are we going to have to do with that? Well, we're going to have to get a 0 on one side. It's probably easier to do so on the right. So I'm just going to subtract 2 from both sides. And then we'd have that 3x plus 1 over x minus 3 minus 2 is less than or equal to 0. So then what we'd have to do is get a common denominator. So it looks like we have to multiply 2 by x minus 3 over x minus 3. So in order to save space, I'm going to do this part horizontally. So we'll have 3x plus 1 over x minus 3 minus 2 times x minus 3 over x minus 3 less than or equal to 0. All right, so then, let's see, we should be able to combine things now. So let's see, I'll have one more intermediate step, I think. So 3x plus 1 over x minus 3 minus, and I'm just going to put that 2 in the numerator. So 2 times the quantity x minus 3 over x minus 3 less than or equal to 0. So then where are we going to end up? Well, we'd have 3x plus 1 minus 2 times the quantity x minus 3 all over x minus 3 less than or equal to 0. I guess distribute the 2. So 3x plus 1 and then minus, and I'm going to distribute the minus 2 this time. I don't usually write it that way. It's probably worth doing. So minus 2 times x is minus 2x, but then minus 2 times minus 3 will give you the plus 6. And that's over x minus 3. That's got to be less than or equal to 0. And then finally, we can combine like terms and say x plus 7 over x minus 3 less than or equal to 0. All right, now we're in business, right? Because then if we're going to set, because now we've got it, right? 0 on one side, single rational expression on the other. And then it looks like our two numbers that are going to break up the number line are going to be -7 and 3, right? Because if you set the numerator equal to 0, that means that you'd have x plus 7 equal to 0. So then x would have to be -7. And then if you set the denominator equal to 0, then you'd have to have x minus 3 equal to 0, which would mean that x would have to be 3. So you've got a -7, you got a 3, and I'm going to make the number line. -7 maybe is here. 3 is here. Okay, so then we've got our intervals that we have to check. So our intervals, that first one is -∞ to -7. The one in the middle would be -7 to 3. And then the one on the right would be 3 to infinity. All right, then we're going to do what we did before. Test value, numerator, denominator, the whole expression, and we should be able to do it from there. All right, so the test value here, something less than -7, I'm just going to pick -8. So in the numerator, we'd have -8 plus 7, which is -1. In the denominator, -8 minus 3, which is -11. So you'd end up with -1 over -11, which is the same thing as 1 over 11, which is positive. And so then I need a big plus up here. And I forgot to do the endpoints. I usually do that first. You don't actually have to do that first, but I usually do. So here, we're actually going to get a closed circle on the -7 because that makes the numerator 0, and that's okay, right? It says less than or equal to 0. Because of the or equal to, -7's all right, so that's part of the solution. The 3 is not, because that just makes the expression undefined. All right, the middle. The middle you can pick 0, so I would. Test value 0. So 0 plus 7 is 7. 0 minus 3 is negative 3. So your expression is 7 over negative 3. Or if you want to rewrite it with the negative out front, is negative 7/3. Either way, that is negative. So negative in there. And then the last one, greater than 3, I would just pick 4. And so we'd have 4 plus 7 is 11. 4 minus 3 is 1. So we're going to get 11 over 1, which is 11, and that is a positive number. So above 3, or to the right of 3 in the number line, that's going to be plus. So what are we looking for? Less than or equal to 0. So less than is in the middle, but we also need the or equal to, so we need to include that negative 7. So what we're going to get for a solution, if you want to write it in set notation, it would be the set of all x such that negative 7 is less than or equal to x less than 3. Like that, right? Notice I got the less than or equal to between the negative 7 and the x to make sure I include that negative 7. Or if you want it written in interval notation, it would be negative 7 to 3 with a bracket on the negative 7 to make sure that we're including that number. All right. Number 3 is, I guess, a step up from here a little bit. It looks kind of innocent. It's not. But you know what we have to do. We got to get a 0 on one side, and then we got to get a single rational expression on the other side. All right. Well, we'll get the 0 on one side then. If you subtract 2 over x minus, or 2 over x plus 2, rather, on both sides, then on the left you're going to have 9 over x minus 5 minus 2 over x plus 2, and that's greater than or equal to 0. Okay, good. We got the 0 on one side. Now the other side, we want to have one rational expression, not 2. So we're going to need the least common denominator, and those two denominators don't factor, right? So we're just going to have to multiply them together to get the least common denominator. So it'll be x minus 5 times x plus 2. So then that means what we're going to have to do is we'll have 9 over x minus 5. Then that'll be multiplied by x plus 2 over x plus 2. Then minus 2 over x plus 2. And then this one will have to get multiplied by x minus 5 over x minus 5. So times x minus 5 over x minus 5. And then that's going to have to be greater than or equal to 0 still. Another thing that I wanted to mention, and this is actually a good place for it. How come we're getting the common denominator and then combining the numerators and not just clearing those denominators out? The reason that you can't do that is because, let's say if you multiplied both sides by the least common denominator, it's unclear what sign that has. Because like if x is bigger than 5 or less than negative 2, it's positive, but in between it's going to be negative. So then it's unclear if you're multiplying both sides by a positive or multiplying both sides by a negative. And if you multiplied both sides by a negative, then you'd have to flip the inequality, so you wouldn't know if you'd have to do that or not. Right? Like that would all be like a thing you couldn't determine. So that I think is worth mentioning here, and it would kind of go right into this step. So we can't clear the denominators since the sign of x plus, or I guess I'm writing it backwards, x plus 2 times x minus 5, is sometimes positive and sometimes negative. So that means it's impossible to determine if the inequality needs to be reversed. Like in a general sense. I mean, I guess you could start breaking it up into pieces and saying, well, if x was greater than 5, then you don't have to. If it's between -2 and 5, then you do, right? So if you did it on a case-by-case basis, you could. That's effectively the same thing as doing the number line. It's just longer. That's why we're not going to pick that option, right? Same thing, but longer. That sounds like a terrible choice. So we should avoid that one, I think. So we'll stick with just getting the common denominator. All right, so if we're going to do that, then now we're going to have, let's see, 9 times x plus 2 over x minus 5 times x plus 2, and then minus, then in this numerator we'll have 2 times x minus 5 over x minus 5 times x plus 2. And let's see, I guess we can distribute the 9, distribute the 2, and combine those numerators together. I'm gonna go horizontal here just to make sure I save enough space. So 9x plus 18, and then minus the whole numerator. So I'm going to put that in brackets, 2x minus 10. And that'll be over x minus 5 times x plus 2. And that should be greater than or equal to 0. And then from there, I think we can do the subtraction. So it'll be 9x minus 2x, which is 7x. And then 18 minus minus 10, which is 18 plus 10, which is 28. So 7x plus 28 on top, x minus 5 times x plus 2 on the bottom. And this will be easier if you factor everything that you can factor. And there is a common factor in the numerator, so we should pull out that 7. And then we'll be left with x plus 4 multiplied by the 7. And then on the bottom, we're going to have x minus 5 times x plus 2. All right. So then, if you set the numerator equal to 0, then you would get that x would have to be -4, right? And then if you set the denominator equal to 0, then you'd get that either x would be 5 or x would be -2. And so we've got to use the -4, the 5, and the -2 to break up the number line. All right. I got to make this one really wide. All right. So let's see if... that's about right. There's -4, and there's negative... Oh, that's... Actually, it's spaced out really badly. Let's see. I forgot there are 3 of them, not 2 of them. I can't space them out quite like that. Actually, I'll do it the easier way. Break it in half, then break those in half. There. Let's say -4, -2, 5. All right. So we have 4 intervals to check. So our intervals, we've got -∞ to -4. Then we've got -4 to -2. And then we've got -2 to 5. And actually, I should space these out more. I already know I'm going to need more writing room than that. Let's see. If I put the other one like flush up against the other side, that's probably smart. And then just try to space the other two. All right. Hopefully that'll kind of work because the thing that we have to simplify is actually pretty big. So we'll see what happens. But then the test values, and then I think, yeah, we'll still just do it with the numerator and denominator and expression. You could just jump right to the expression if you wanted to, but this expression has a lot going on. Might be easier just to do the numerator and denominator individually. So first interval, I would pick -5, right? We gotta have something less than -4. Oh, and I need to include an endpoint because we have a greater than or equal to. So I've got to include the -4 because that makes the numerator 0. So filled in circle there, but then open circles at the -2 and the 5 because those just make the expression undefined. Okay, now back to that -5. All right, so in the numerator we're going to have 7 times -5 plus 4. So it's 7 times -1, which is -7. Then in the denominator we're going to have -5 minus 5 times -5 plus 2. So that's -10 times -3, that's 30. So it looks like we're going to get -7 over 30, which is negative. All right, so we're going to need a big minus down there. All right, in between -4 and -2, well, if you stick with the idea of picking an integer, you only got one option. You'd have to pick -3. So no reason to make this more complicated. The numerator would be 7 times -3 plus 4. That's 7 times 1, which is 7. And then the denominator is going to be -3 minus 5 times -3 plus 2. That's -8 times -1, so that's 8. So we're going to get 7/8 for the expression. That is positive. All right, so we're going to need a big plus between the -4 and the -2. Next interval between -2 and 5. This is the one where you can pick 0. Might as well. So 7 times 0 plus 4. That's 7 times 4, which is 28. And then we'd have 0 minus 5 times 0 plus 2. That's -5 times 2, which is -10. So we're going to get 28 over -10. I guess you could reduce this if you felt like it and say, well, that's the same thing as -14/5. The important thing is that it's a negative number. So negative. And so I need a big minus in between -2 and +5. And then for above 5, I would probably just go ahead and pick 6. And so then we'd have 7 times 6 plus 4. So that's 7 times 10. That's going to be 70. And then 6 minus 5 times 6 plus 2. 1 times 8. That's 8. So it looks like what we're going to end up with is going to be 1 times, yeah, so 70 over 8. And so then that, I mean, if you want to reduce that, you can and say, well, that's 35/4. The important thing is that it's a positive number. And so that means we got a plus down there for that last interval. So plus there. And we were looking for greater than or equal to. So we need those two greater thans. We're going to need this. We're going to need this. And then we just also got to make sure we remember to include that -4 because of the or equal to 0 part. All right. So then our solution. If we're going to write it in set notation, it would be the set of all x such that -4 is less than or equal to x, which is less than -2, or x is greater than 5, right? One of those. Or if you'd prefer this written with intervals, it would be -4 to -2 with a bracket on the -4, union 5 to infinity, like that. All right, there is one other thing I want to mention here, which is that it looks like the signs always alternate. Like how here, minus, plus, if you go left to right. And if I scroll up, number 3, they alternate. Or number 2, rather, they alternate. Number 1, they alternate. They don't always alternate. The thing that would stop that from happening is if you had one of those, because how there are all these binomials showing up, if one of those was squared. Or really if it was to any even power, but really, I mean, if it was going to show up, it'd probably be squared. So like here, if instead of having in the denominator, instead of an x plus 2, if we had an x plus 2 quantity squared, then there would be no sign change there. Because then like the part that's being squared, like that's always a positive no matter what. So then you don't get the alternating. I don't think that's going to happen. I ran the homework assignment a couple of times and it never came up. So I think you're always just going to have multiplicity 1, which means that you don't get, you know, a root repeating. You don't get like an x minus 5 times another x minus 5. You just have one of them. And if all the binomials are just raised to the first power, then yeah, you do get the alternating signs. So that's actually a thing that you can use as a check, right? Because if you don't have binomials getting squared, but then you're not getting the alternating signs, there's probably an algebra error someplace, right? You probably have a sign wrong somewhere, something like that. So it actually does work as a check. All right, and the next thing, number 4, honestly is easier than number 3. It's the same kind of thing, but I wanted to have one phrased this way, just because they look a little bit different. But if you can do 3, you can do 4, because the hard part of 3 is already done, right? Because in 3, if I scroll back up, we didn't have a 0 on one side already, right? We had to first move that one rational expression, and then we had to get a common denominator and combine them together. Look at where 4 is in that process. You already got a 0 on one side. The other side has a single rational expression, and not only that, its numerator is factored. So that one's factored as far as you can factor it. So you could jump right to saying, okay, well, what are we going to use to break up the number line? So 4 is like 3, but it's actually way shorter. So like if you were going to set the numerator equal to 0, then we would have 2x parenthesis plus 1 times x minus 1 equals 0. And let's see, from setting that first part, the 2x plus 1 equal to 0, you get that x was negative 1/2. And from the second part, you get that x was 1. And then if you set the denominator equal to 0, then you'd get that x plus 6 equals 0, which would mean that x is negative 6. So we got to use negative 1/2, positive 1, and negative 6 to break up the number line. All right. So I need a big number line again. All right, I guess negative 6 would be the smallest out of those 3, and then the negative 1/2, and then the 1. Okay, so we're going to do the same dance we were doing before. So we've got our 4 intervals, since we've got negative infinity to negative 6, and then we've got negative 6 to negative 1/2, and then we've got negative 1/2 to 1, and then at the end we've got 1 to infinity. All right, so then the test value, and then the numerator, and then the denominator, and then the expression. Okay, test value for that first one, less than negative 6, I would pick negative 7. So then you'd have 2 times negative 7 plus 1 times negative 7 minus 1. Let's see, that's going to be negative 14. It's negative 13 times negative 8, which would be the same thing as 13 times 8. Let's see, which should then be, and actually, yeah, okay, I have this set up right. So this 13 times 8, that's 104. Yeah, 80 and 24. And then the denominator, we'd have, oh, this at least this one's easy. Negative 7 plus 6 is negative 1. All right, your expression's 104 over negative 1, which is negative 104. That's a negative number. All right, next, between negative 6 and negative a half, anything in there will work. Negative 4. That's in there. So the numerator, you have 2 times negative 4 plus 1 times negative 4 plus 1. Let's see, that's going to be negative 7 times negative 3, so that's 21. And then I don't need to write denominator. I just need to write what it is. Negative 4 plus 6 should be 2. So the expression is going to be 21 over 2, and that is positive. All right. So that one's positive. Oh, I didn't put the big negative in there. So big negative here, big positive here. And the endpoints here, we don't even need them because it's a strict inequality. So automatically, these are all going to be things that we don't worry about. Between negative a half and 1, 0, right? Pick the 0 when you can. So 2 times 0 plus 1. Oh, wait. This should be a minus. Oops. So that's a minus. Then that's, well, it's negative 7 times negative 5 is 35. So I had a sign wrong there, but it's actually not really going to affect anything because that's still going to be a positive number. We have 2 times 0 plus 1 times 0 minus 1, and that's negative 1 because that's 1 times negative 1. And then you'd have 0 plus 6, which is 6. So it looks like we're going to get negative 1/6, and that is a negative number. And so we're going to get a big minus in between negative 1/2 and positive 1. And then the last one, pick something bigger than 1. I would just pick 2. So if x is 2, then the numerator will be 2 times 2 plus 1 times 2 minus 1. So that's 5 times 1. So that's just 5. And then the denominator is going to be 2 plus 6, which is 8. So then we're going to end up with 5/8, and that's a positive number. All right, so last interval, that's a plus. And we were looking for where we got values that were negative. So there and there. So less than negative 6, and then between negative 1/2 and positive 1. So our solution, it would be the set of all x such that x is less than negative 6, or negative 1/2 less than x less than 1. You can write it that way, or if you want it written as intervals, negative infinity to negative 6 union negative 1/2 to 1. Either way. And we're not going to include any endpoints here. It was a strict inequality, right? I mean, you wouldn't include the negative 6 anyway because that would just make the expression undefined, but the negative 1/2 and the positive 1 are going to make it equal to 0, but we get a strict inequality this time, so we don't want that. That's not going to be part of our solution. So see, 4 was like 3, but it's faster because like the early part of 3 is kind of already done since you got the 0 on one side and the single rational expression on the other. All right, number 5. Number 5 is a word problem, and the solving here is actually not too bad. So we have that function c of x, which is supposed to represent the daily cost of manufacturing x bicycles. So like x is the number of bicycles that get manufactured during a day. So the average daily cost, like the average per bicycle, would be 80x plus 5950 divided by the number of bicycles, which is x. So then how many bicycles must be produced each day for the average cost to be no more than 150? So no more than 150 means it can't be bigger than that. So equal to 150 is all right. Less than 150 is all right. So that means that we need C bar of x to be less than or equal to 150. All right, well, we know what C bar of x is, right? The formula is right up there toward the top, so we can say, all right, well, then we need 80x plus 5950 all over x to be less than or equal to 150. But this is kind of like what we were just doing, right? We need to get a 0 on one side, probably the side with the 150 on it. And then from there, we'll have to get a common denominator so we can end up with a single rational expression on the left. So I'm first just going to subtract 150 from both sides. And then we're going to get the common denominator, so I'll have to multiply that 150 by x over x. And we'll end up with 80x plus 5950 all over x minus 150x over x less than or equal to 0. All right, so then we can combine the numerators and say 80x plus 5950 minus 150x all over x is less than or equal to 0. We could combine terms, so 80x minus 150x, we'd have negative 70x plus 5950 all over x is less than or equal to 0. But the way the function is set up, because it looks like what we're going to do is we're going to say, okay, well, we need 0 because that makes the denominator 0, and then we just have to figure out what number makes the numerator 0. Actually, we don't have to worry about the denominator because the way that this is set up, x is the number of bicycles getting made. It's not going to be negative, and it's not going to be 0, right? It's going to be some positive number. So since x is the number of bicycles manufactured, x must be positive, right? It can't be 0 because it's in the denominator and then you'd be dividing by 0, but it also can't be negative because that doesn't make any sense, right? How do you make negative 15 bicycles? So if x is positive, the only way you could get that expression to be negative would be if the numerator is negative. So for negative 70x plus 5950 over x to be less than or equal to 0, negative 70x plus 5950 must be less than or equal to 0. Right? If the denominator is positive, then the only way you can get a negative out of that whole expression would be if the numerator is negative, right? So then we just have to solve that, right? So, all right, we'll go back to blue, I guess, and say, well, now we just have to solve negative 70x plus 5950 less than or equal to 0. Okay. Well, then if you subtract 5950 from both sides, you get negative 70x less than or equal to negative 5950. Be careful. You got to divide by negative 70. So if we're dividing by a negative, we got to flip the inequality around. So negative 70x over negative 70 would then be greater than or equal to negative 5950 over negative 70. And 595 divided by 7 is 85. So this is actually that x is greater than or equal to 85. And so then the answer, I barely have enough room for this, but the answer would be at least 85 bicycles. That would do it. All right, so this one, it's another rational inequality, but because this is a word problem, and just based on the context, you go, wait a minute, x can't be negative. So the way that the solving works ends up changing a little bit because of that, right? Because then we could just kind of ignore the denominator and go, well, that has to be positive, so we just have to look at the numerator. And then it became a linear inequality, which was nice, right? Those are easier. So that worked out for the best, I suppose. But there is one, I think there's one word problem at the end of the homework for this section. They tend to look kind of like this. So I think this ought to be pretty similar to what would show up there. And I think that would cover all of the possibilities that might show up in section 5.5 with the rational inequalities.